All right, so today we're going to do a lesson on congruent transformations. You've probably, if you're watching this, you've probably dealt with these many, many times before, all right? And we're actually going to come back to these reflections, translations, or rotations later in the year, and we're going to do some way more stuff with them. So this is kind of just an introduction to that, okay? I will tell you that probably the hardest thing that people have with these types of problems is sometimes it's hard to tell if something was a translation or a reflection. And sometimes it's even hard to tell if it was a rotation or not, like which one it was. And I disagree with the book all the time on these, so just be careful with that. It's sometimes hard to tell what it could be, so just take your time with that part. All right, so let's talk about each one. So there's three types of congruencies, right? There's three types of transformations that keep congruency, right? Translations, which you worked with in 7th grade probably. Remember how we translated graphs, right? Right? And what's the other? Rotations and reflections. Math team, we learned these. These three are special. They have a special name. Transformations that keep congruency. Isometries. It's not that important that you know this, but the isometries keep congruency. Later in the semester, I think next semester, you're going to learn about dilations, which is making the shape bigger and smaller. And that is not an isometry. Yeah, these are the three isometries. When you translate something, when you rotate it, or when you reflect it, it keeps congruency. Because it's still the same shape and size. You're just moving it around, yeah? All right. So, I think this picture's bad. Isn't this picture bad on example A? I think it is. Yeah, it's so bad. It needs to be like this. So fix the picture, please. All right. All right, so the first one, letter A, if you fix the picture, that's a reflection. You can't see my hands right now, but if you hold up your hands, right, put your thumbs together, your hands are reflections of each other, unless you got some kind of genetic disorder or you lost it in a shark accident. Yes? Yeah? They're reflections of each other. A nice way to tell if something's a reflection, if you're really struggling with a reflection, is the fold test. There will be a line, if it is a reflection, there'll be some line that you can draw that will fold it straight in half. In this case, it's the y-axis, yeah? And if you folded it together, right, this point right here would be touching that point if you folded it together. Yeah? So if you're ever struggling, hey, is this a reflection or not, sketch it out, fold it together literally, and see where it's at. Yeah? All right. So that's a reflection. The second one, what are we doing? We're just moving it. Later in the semester, we'll do vectors, which are translations, okay? But we're just moving it, yeah? And then the last one, a rotation. Later on in the semester, we'll get into rotations, and you'll have a point of rotation. I don't even know where that point of rotation is. It's actually not that easy to do, all right? I don't think it is origin, actually. It could be. Maybe it is origin. Yeah, 90-degree rotation, that might actually be origin. It gets harder and harder to prove. That's not what this lesson's about, but that's a rotation, right? All right. So let's look at these. All right, so what type of transformation it was, all right? Be careful. You can get an answer quickly and miss it. What looks like happened? Reflection. So for sure that's a reflection, right? Is that a translation? No, obviously not. The one you got to be careful with, is that a rotation? Could it possibly be a rotation? One of the, you probably don't remember this, but one of the tests for giftedness is they give you a test like that and they say if you rotated it, what would it look like? Yeah? And some people have a very hard time with that because they don't have spatial sense. All right, they're good at something else, but they're not good at that. Yeah, that is one of the ways. If I rotated it, go ahead and do a little sketch off to the side. If I rotated it at 180 degrees, what do you think it would look like? Draw it off to the side. It's actually one of the tests of giftedness. Is can you visualize what that would look like? And it wouldn't look like that. It would look like a 7, right? It would look like that, right? If you rotated it. So that's not a rotation, it's just a reflection. You with me? All right. Number 2. For sure it's a translation, right? So we know it's a translation. Anything else? What about a reflection? See, at first glance, you might say no, but check this out. All right. Possibly, I don't know this for a fact yet, but could it be reflected over something like this? Now watch. What you would have to do, and you're going to learn this later, is that is matching up with that, right? See how they're the same distance from that line? This is matching up with this, yeah? So that, can you picture this? This shape is getting rotated like this. It's way easier on your piece of paper if you take it and you rotate it 180 degrees and just start doing that and seeing if everything's matching up. Yeah? If I do that little fold test, what's this going to go to? When I fold it, this is the line that I'm folding it on, right? That looks like it's going here. Could it be a rotation? It's harder to tell. I'm 99% sure. And if I wasn't sure, what I would literally do, I mean, there's a way to do it mathematically later on, but what I would literally do is draw a little picture of this, right? You can put a piece of paper over the book, draw it out, and then what? Fold it and see if it works. I'm pretty sure that is a reflection. It can be multiple things. Could it be a rotation? You sure? I mean, what if the point of rotate, so try it. How far can you rotate it to make that shape? You need to make it end up in quadrant 4. If you rotated it, I think it's wrong. What would it look like if you rotated it 180 degrees? This point would end up down here, right? So that point would be down there. It would look something like this, I think, right? Like that, kind of like that. Or that pointy part is at the bottom. All right, so we're sure it's not a rotation, yeah? But I'll tell you, be careful, because you might think something quickly, and it might be something else. 3? Is that a reflection on 3? Over what? All right, for sure that's a rotation. And I don't think it's anything else. It's definitely not a translation. All right.
Isn't it? Because there's only one square from it to the y.
But so for a translation to happen, right, it has to just be pushed somewhere else, right? So this shape would stay like that, and you would move it over here. And if I moved it over here, it would still look like this. How would I make the shape go upside down? I'd have to twist it, which is a rotation. So when I do it, that's a good question. See how this shape could have gone straight down to there? I could just move it straight down there. That's a translation. So that's a good question. What's up? It's hard to tell sometimes. There's a method to figure out where the point of rotation is. I'm gonna guess it's somewhere over here, but it's definitely not origin in this case. Okay. I'm thinking it's somewhere over there. So. It's not what we're going to get into right now, all right? 4, what's that look like? Only a rotation. 5, let's give some order. Translation for sure, just slide it right over, right? Rotation?
Yes.
If you rotate at 180 degrees, that would not make itself, right? Or 90 degrees even. Rotate that 90 degrees, it would end up, 180 would end up down here. So 90 would make it there. Well, you can't do a 360 rotation. Oh, it's always rotation. Rotation for sure. And could it be a reflection? For sure.
Why could you have a 360 rotation?
It'd be itself.
So everything could be rotation.
Right, that's the joke we just made. All right, last one. Could that be is that a translation? Let's start off easy. No. Reflection?
Yes.
For sure. Rotation. Play a little game. Right below it, draw what it would look like if you rotated it.
No.
Draw what you think it would look like. It's tricky, huh? Would it be that?
No, it'd be like.
I think this piece really tricky. This is a much. I might actually mess this one up. So let's see. So I'm going to rotate it. So it's going to end up here. But I think it's like, is it this?
Yeah, something like that.
I think it's like that.
Yeah.
Yes.
It's
If you ever get online, it's fun. You know, most of you are in this class because of passing the gifted test, right? And there's problems like this where you have to do them, right? For high IQ societies, like Mensa is a high IQ society, not above average IQ, but a genius level IQ. Those problems, they start dealing with what?
This is from Girls Athletics
For
for Helen.
who?
For Helen.
Oh, thank you. Appreciate it. Thank you. One of the tests for giftedness, high IQs, is doing much more complicated. Hey, what would happen if you rotated this 90 degrees and translated this and rotated it and reflected it here? Yes? And it gets much harder. I've seen problems. If you ever wanted to make your brain hurt for a while, get on practice Mensa tests, right? High IQ tests. I've seen them where they'll take the shape on the ceiling, right? One of those complex ones. They unfold it with colors, and they'll say, if you put it back together, what would it look like? And you're like, they all look like it. You're like, right. Welcome to the difference between being smart and super smart. Yeah? It is a translation. I'm just taking this point, moving it here. I'm taking that point, moving it here. I'm taking that point, moving it there. See what's happening? I'm just taking the whole shape and moving it to the right.
You did a 180 degree rotation on number 6, right?
I don't know. Did I?
Yes. Yes.
Huh? Well, yeah, but the point of rotation could be over here, and it would do the same thing. You don't know where the point of rotation is, but it could end up right below it with the right type of setup. You just don't know where the point of rotation is. The point I'm making, though, is no matter how I do this, it's going to end up here, not there. It's not a rotation. Okay? It's tricky because there's a point of, we're not getting into this, but there's a point of rotation, right? Like, you kind of picture it, you have a piece of paper, you put your pencil on down there, that's the point, and you swing it around. There could be a way you could make a piece of paper to swing it around to be this. That'd be like the hinge point is what I call it, yeah. But it's not here, obviously.
No.
It's, my gut is it's over there somewhere. I'd have to play with it. That's not what we're getting at here, so. All right, let's go on to the next part. Okay, so this is important, all right? If they say this is a transformation of this, then that means that W goes with R, X goes with S, and Y goes with T, yeah? So W goes with, what did we say, R? S goes with what? Okay, so look for how they're congruent, because that'll help you to tell sometimes if it's a rotation or a reflection. All right? All right. So what do we have? Graph the original and its image. Identify the transformation and verify that it's congruent. Well, how could I verify that it's congruent? I know you might be saying, well, I just look at it. No. How do we prove triangles are congruent?
Measure the distance between the
Sides.
We can prove side, 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 angle, sides, angle, angle, side, angle, side, angle. You don't know the other one. Hypotenuse, leg is another one you can use. Because if you prove the hypotenuse is equal to a hypotenuse and a leg is equal to a leg, and you know this is a 90, then the third side has to be equal by Pythagorean theorem. That's called hypotenuse leg. Yeah? We don't touch it in this book, but other books do. So that's another way you can do it. I think that the two easiest ways is prove that this side, TS, is equal to XY. And you can just physically count them. 1, 2, 3, 4, 5. That's a distance of 5. That's a distance of 5. Right? Prove the bottom. 3, and that's 3. And from there, you could do the distance formula to prove TR is equal to YW, but there's an easier way. You could do Pythagorean theorem to get the third side. Yeah? But you can't use Pythagorean theorem because you haven't proved that it's a right angle. Right? That's a right angle, that's a right angle. Later on in the semester, they're not going to tell you that it's a right angle, and you're going to have to prove it by doing slopes. What you would do, we're not going to worry about that today, but you'd have to prove that that slope is perpendicular to that slope. And if it is, then that's a right angle. And that's not hard. The slope of that line is 0. The slope of that line is undefined. Those are perpendicular. Right? So that's a right angle. So what do I have now? What's proved here? You could use Pythagorean theorem now, but you already have side angle side. You're done. Right? Side angle side proves they're done, right? So graph the original and new. We did it. Prove that they're equal. We did, right? 3, 3, 5, 5, and that's a right angle. So side angle side, right? All right. Let's do this again. I think they already graphed it for us, right? Oh, we didn't identify it. What is it? Translation, right? All right. What's this next one? Could it be a rotation? If these were equal, then yes, it could have possibly been a rotation. But since this is 3 and this is 2, no, it's not going to work, right? All right. So that's definitely a reflection, right? And what's the distance from A to B? We have to prove, graph each, identify the transformation, and verify it. All right, so how long is AB?
2.
2. ED is 2. BC is 3. And 3. And we know that's a right angle. So that's enough for side angle side, right? We know those triangles are congruent. You could do the third side if you wanted, and do side, 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 which most people would probably do. I'll probably do that on the next problem. And so that proves that they're congruent. Right? And what's the transformation? Reflection, right? All right. All right, next one. All right, so let's go through it. It's for sure a translation, right? Could it be something else? What? I don't think it's going to be a here's why it's not going to be a rotation. See how this is 2? These are not 2. Now these look like they might be equal, but if I rotate that piece is not going to end up on the bottom anymore. And that's these pieces are equal, right? Because this is 2 and this is 2. Yeah? All right. All right. Yeah, there's not a reflection either. No. The reflection would be fun to draw for that one. It would be, actually, it would be here. It would be there if I reflected over this line, right? And then you start sketching out the rest. There's a cool little way you can do this. All right. What else do I want to have to prove then? I need to know what how long QR is and how long RS is, right? And I guess I got to do TU because I can't measure these and I can't use that right angle that I just did, right? UV. All right, so let's do these. QR. Difference of the x's. How far from Q to R? Distance between the x's? 1, right? Distance between the y's? So that's 1 squared plus 2 squared. So that's what? Root 5? 1 squared plus 2 squared is not 3 squared. Root 5. The next one, RS. Well, isn't that 1 and 2 again? So root 5. And all I have to verify is it 1 and 2 again, right? Going from T to U, that's a distance of 1 on the x and a distance of 2 on the y. So root 5. They're all root 5, which proves what? It's a translation, and you could even say the reason, right? What was the reason for this? Was what, side angle side? I don't know if they're going to ask you that. What's this one? Side, 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 right? All right. Not hard. A little bit tedious, but not hard. All right.